So let us begin first with the case of multiplexers. What is a multiplexer? In general, a multiplexer means many to one. A multiplexer, which is many times abbreviated as MUX and pronounced by many people as MUX, you can call it a device that can receive multiple inputs, just like what you see here. So you've got multiple sources here, source A, B, C, up to Z in this example. And it can synthesize a single output. What is important to note is that this single output is synthesized in a recoverable manner. Now, let's give some examples that may explain this better to you. Suppose that you want to fetch a data bit from a computer memory. How would you do that? Well, if you used a multiplexer, the multiplexer would allow you to specify an address, which you would have done with your source selection with an input code, and the particular memory bit would have been returned to you. So if you have a memory, let's say, of 256 cells, you want to connect it to an output pin. If you want to select any of these 256 bits, then you will need a particular input selection here. And as we're going to see, this would be 8 bits. As you can understand, if you have 256 memory cells, you need 256 different memory addresses. So the source selection here is 8 bits so that you can synthesize any of these memory addresses here, which would be a power of 2, starting from 0 all the way to 2 in the power of 8 minus 1. Let's get back to our example. You got different data sources, as we said earlier, from source A, B, C, all the way to a final source here. Let's call it source Z. You also have a source of selection. This is the control signal. What happens is that based on the control signal, you're going to select which source is going to be outputted. Now, this is the block diagram symbol of a MUX, a multiplexer. Now, the question to you is, having said what we said earlier, if we have 16 different inputs, how many bits do you believe you would need for the source selection? The simplest case of a multiplexer we can think of is a multiplexer that takes 2 inputs. And as you can understand, the selection here, if it is 0, then we define that the final output would be equal to A. Likewise, if it is equal to 1, the output would be B. So therefore, if you have a 1-bit multiplexer, you need 1 bit for the selection. Now try to think via induction how many bits you would need for the selection if you were dealing with 16 different inputs. But even the most simple case of a multiplexer, the one that we defined in the previous slide, needs a little bit of more lateral thinking. So again, we see here that we got a 2-input, 1-bit multiplexer. This would be the truth table, which would include the 1 bit for the selection for the control, inputs A and B, and the output C here. Using all the different combinations over here of selection A, B, and C, we managed to fill in this truth table, which will obviously have 8 different rows. Now, depending on the selection, the final output here will be either equal to A or B. If you treat C over here, the output, as a function, then you compute here the mean terms. And obviously, you can construct a Carnot table. Now, how would that Carnot table look like? the first mean term that we're going to use is mean term 2, because the output function is equal to 1. Obviously, mean term 3 follows, mean term 5, and the last mean term 7. Now, following the process that we have explained in the previous lectures, this is how the function would look like. It would be the selection dash times A or selection times B, which states the obvious. If the selection is false, then the output will be equal to A. And or if the selection is true, the output should be defined by B, input B. Now, converting that into a circuit, this is how it will look like. So a 2-input 1-bit multiplexer is as easy to define as this. The process that we followed to define it went through the truth table here, finding the mean terms that we are interested for, putting them in the Carnot table, finding the minimized function, and then converting it into a circuit. Now, as you probably should easily recognize by now, these two circuit versions are equivalent, and the reason is De Morgan's. We replaced the final OR gate here with an and the previous AND gates with NAND as well. Now let us see how a 2-input n-bit multiplexer would look like. So this is a 2-input 1-bit multiplexer, as you know. If you chain it with another 2-input 1-bit multiplexer and all the way through to an nth 2-input 1-bit multiplexer, you will have this result. Now, each and every of them, depending on the control that you apply, would be outputting a different C value, C0, C1, all the way to Cn-1. Overall, you've got n different pairs of A's and B's and n different outputs from 0 to n-1. Notice that instead of complementing the selection bit inside each and every 1-bit multiplexer, what you see over here, it is possible to feed each 1-bit multiplexer with selection and selection dash. That is again the same circuit with some parts missing. Now notice what happens here. Essentially, we're passing the same selection as it is for the other multiplexers. So essentially, what we're doing is what you see over here. This slide is going to help us understand better what you've seen in the previous slide. What it shows is an enabling bit and a selection bit here. Remember that one of the goals that we set in the previous slide is that we are going to avoid having to negate in each and every multiplexer here chained the selection bit. Let's try to understand how this works by example. Now, this enabling bit over here is an active low pin, which is used by this 2-input 4-bit multiplexer, which conforms with MSI 74X151. This means that if the enabling bit is equal to 1, it will disable the whole multiplexing scheme. As you can see here, the result, regardless of what the selection bit is going to be 0, 0, 0 in the output. All that if we assume that the enabling bit is equal to 1. It's like enabling a mechanism that disables the whole multiplexing. All right, Now in this next slide, let's see what happens if the enabling bit is 0. In this particular case, the outcome of these two gates over here, the AND gates with negated inputs, will be S dash and S. So you already have the selection bit and its complement. And you pass it appropriately to each and every multiplexing scheme that you have here. Let's see what happens in the first part of the circuit that multiplexes the two first bits. You have S dash times the first bit of the first word, and then you got S times the first bit of the second word. Obviously, what happens here is that if the selection bit is 0, the result is going to be the bit that comes from the first word, and the other way around. If the selection bit is equal to 1, then the first bit result will be from the first bit of the second word. And this is how it works for all the different input bits in the previous slide. Now let's proceed with the other extreme example that we can have. In this case, you have n different inputs of 1 bit each, which are being multiplexed so that you get 1 bit as an output. But in this particular case, we will need m different bits so that we select which of the inputs we want to be selected and outputted. Obviously, there is a connection between n, which is the number of input bits, and the selection bits over here. Let's, before we reveal the answer, think of what would happen if you had 256 different inputs here. How would you pick? Imagine that each and every one of these bits would be identified by some sort of an address, starting from 0 all the way to 255. All right, so how many m different bits you would need to choose one of these addresses from 0 to 255? The answer is 8. And in the general case, if you have n different inputs, you need at least m bits such that 2 in the power of m is greater or equal to n. So you can have more bits than you need, but you cannot have less bits that you need for the selection process. Now in this slide, you see what happens if you summarize things having 1, 2 selection bits and 4 different inputs. If y is the output and you have the enabling bit being equal to 1, then obviously you don't care about the inputs here. The output will be always 0. Also, the output will be 0 in the case that the enabling bit is 0, but the rest of the combinations here are 0. All of the inputs are equal to 0, and the selection here is this. Overall, the selection bits and the input bits are 6, which gives you 2 in the power of 6 combinations. If you try to extract the truth table, you don't need to write all the different combinations 2 in the power of 6. If you think of it, if the enabling bit is equal to 1, you don't care about the selection, the output will always be 0. So we do need to take a look at what happens when the enabling bit is equal to 0, and check out what happens with the different combinations of the selection bits. If you have 2 bits for the selection, obviously you're interested in 4 different combinations of them. And we all know that the output should be, in the first case over here, where the selection bits are 0, 0 should be the first bit that comes in, then the second bit, the third bit, and the fourth bit. If you try to think how you would express this in terms of Boolean algebra, well, this is how it would look like. You would have the following. you would need the negation of the enabling bit, of course. You would need the bit that you would like to extract, of course, and both of them chained with an AND. And you need the AND operation of all that, in this case with the negation of both selection bits, in the second case with the negation of the first selection bit and the second bit. Then here you need the negation of the you need the first bit and negation of the second bit. And here you need no negations at all, you want them both to be true. And this is the result that it gives you. You have an AND operation between the first bit and this combination over here, this line, all the way to the last line over here, that you got the final bit being inserted into an AND gate, that the other input should be equal to what you see here, the enabling bit being false and the two selection bits being equal to true. Now, putting everything together, this is how it would look like. And at the end, you just need a big OR operation for the result of the multiplexer. And with all that, we reach finally to demultiplexers. Obviously, the work that the demultiplexer does is the exact opposite of what a multiplexer does. So suppose that you would have here a multiplexer. It would get some source inputs. There will be also some source selection, and that would be outputted and used as input to a demultiplexer. The demultiplexer, as you can imagine, does the exact opposite job. It gets the input based on a destination selection. It will try to output what was the original selection here in the multiplexer. Remember that when we've given you the definition of a multiplexer, we said that it is a device that can receive multiple input signals and synthesize a single output in a recoverable manner. So essentially, a demultiplexer is capable of recovering what was the result of the synthesis here. One final thing to say here, since everything uses the reverse logic with demultiplexers, the number of bits that you need for the destination selection is m, and that m bit word has to be within with n being less or equal to 2 in the power of m again. Only this time n is not the input, but it's the output, it's the destinations. And with that, we've reached to the end of this week's video. Remember that everything is closely related between weeks 10, 11 and 12. We are currently in week 11. In week 12, we're going to talk about decoders and encoders as well as about arithmetic logic unit. And there you will see how decoders and encoders can be related to multiplexers and demultiplexers.